We will now talk about the support of a distribution. Okay, so given a function f, you know what the support is. Support of f is the set of all x in omega or whatever the domain is, such that fx is not equal to 0, and then we take the closure. Okay. Now we want to extend the notion of a support to that of a distribution, but we immediately run into a difficulty, namely a distribution is defined on an open set. Okay, it's a continuous linear functional on the space of C infinity function with compact supports. Therefore, it is meaningless to say the value of a distribution at a point. That has no meaning, that statement. So how do we then extend this relation? So we can equivalently say the support is equal to the complement of the largest open set where f vanishes. So it's easy to see that these two are the same. So the complement of largest open set where f vanishes, the complement will be a closed set, and you can say that will be precisely the closure of set of all x such that fx is not equal to 0. Now the second statement is amenable to us for generalization. Okay, so we want to know, given a distribution T, so omega in Rn open set and T belong to d prime of omega. Now we would like to say if omega naught is a subset of omega open again, then we want to know how to define T restricted to omega naught. Okay, does this have a meaning? Okay, so this is what we want to say. So omega naught, so let us take phi belong to d omega naught. We have to define the this object on all such functions. Now you take phi tilde equals extension of phi to all of omega by 0. So you have omega here, you have omega naught here, this is omega, and so in all this region you put phi equal to 0, and therefore that is called the extension. So phi tilde equal to 0. So phi tilde equal to phi on omega naught and equal to 0 on omega minus omega naught. Okay, so now this, it is clear that phi tilde belongs to d of omega, because all that we have done is extend it by 0. The support of phi is a compact set contained inside omega naught, so near the boundary, fairly close to the boundary, omega phi will be 0, and you are further extending by 0, so there will be no difficulty for the continuity of the derivatives and so on, and therefore you have that phi tilde belongs to d of omega. Now if phi n goes to 0 in d of omega naught, then phi tilde n will automatically go to 0 in d of omega, because the support of phi tilde n is the same as the support of phi n, which is they are all contained in a fixed compact set K, and on that compact set K everything goes to 0 uniformly, all the derivatives, etc., and therefore this also implies this. So now we define T restricted to omega naught acting on phi is nothing but T acting on phi tilde. Okay, so this way we define, so this just says that d of omega naught is included in d of omega in a continuous fashion. This hooked arrow means that the inclusion, it's an set inclusion which is also, and the inclusion map is continuous. Okay, so we define this for all phi in d of omega naught. So in this way we can extend the define what do we mean by T restricted to an omega set. So now let omega contained in Rn be open and omega I in I, family of open subsets, open subsets of omega, and we write omega tilde is the union I in I, omega I. Okay, so assume T restricted to omega I is 0 for all I. Then we claim that T restrict to omega tilde is also equal to 0. Okay, so how do we do that? So let us take phi to be in D of omega tilde. Now, so support of phi equals a compact set. Okay, so now you take psi I in I, locally finite C infinity partition of unity, subordinate to omega I in I. So what does it mean? Support of phi I is contained in omega I, support of phi I in I is locally finite, psi I is in C infinity of omega, and 0 less than equal to psi I less than equal to 1, and finally sigma I in I psi I of is identically equal to 1. So this is the locally finite C infinity partition of unity, which we know always exists. Now K, for every x in K, which is the support of phi, there exists a neighborhood Ux which intersects only a finite number of the support of phi I. Okay, now so K is then covered by these things, union x in K, Ux. But then K is compact, so there exists a finite subcover. So there exists a K can be written as subset of union I equals from 1 to small n of U of xi in K. So each of these U of xi's will intersect only a finite number of support of phi I. So this implies that K intersects only a finite number of support of phi I. Okay, so therefore we can write phi equal to sigma I in I phi psi I. This is well defined because again for each element in x in K, it will only intersect a finite number of support of phi I. So this is essentially only a finite sum. Now phi psi I belongs to D of omega I, because psi I is C infinity with support in omega I, phi is a C infinity function with compact support. So the product will have compact support and it will be contained in the support of psi I, which is contained in omega I. And also you have phi tilde, the extension by 0 is nothing but sigma I in I phi psi I tilde. So now we have T of phi tilde is equal to sigma I in I T of phi psi I tilde, and T of phi psi I tilde is nothing but T restricted to omega I of phi psi I and that is given to be 0 because t restricted to omega I is 0. So this, each of these terms, which is only finite number of them, can be non-zero, and even those are all 0, and therefore t of phi tilde equal to 0. So this implies that t restricted to omega tilde is 0. Okay, so if t vanishes on a certain number of open sets, then t vanishes on their union. So it makes sense to say there is a largest open set on which t vanishes. Okay, and consequently we can make the definition: omega contained in Rn open set, t belongs to d prime of omega, then support of t is the complement of the largest open set where t vanishes. So this makes perfect sense now, and therefore the support is again a closed set. So let us take example. F is in L1 log of omega, then Tf of x is nothing but Tf of phi, sorry, is integral f phi dx over omega, and clearly now this will vanish. Wherever f vanishes, this will also vanish. On every open set where f is 0, Tf will also be 0. Similarly, and therefore the support you can easily check. So support of Tf is nothing but the support of f in the classical sense. So this is for the function, nothing changes. Okay, now let us look at one more example. Delta equals Dirac distribution on Rn or Rn, let's say, and then you have support of delta is in fact equal to singleton 0, because if you take Rn minus 0 and you take phi, which is such that support of phi is contained in Rn minus 0, then phi of 0 is 0. This implies that delta phi is 0. So Rn minus 0, but if you have Rn, then you can have functions which don't vanish at 0, having compact support and being C infinity, and therefore t will not vanish. So the largest open set where delta vanishes is Rn minus 0, so its complement is singleton 0, and therefore support of delta is singleton 0. And in fact support, you can check this also, d alpha delta is also singleton 0 for every multi-index alpha. Okay. So now if t is such that support of t, which is always a closed set, is compact, we say T is a distribution with compact support. That is natural. So let us take a closer look at distributions with compact support. So let us assume that support of f is locally integrable and support of f equals k compact. Now if you take psi belong to C infinity of omega, then integral f psi dx on omega makes sense, because the integral is essentially only over a compact set. Psi is bounded on a compact set and f is locally integrable, therefore f is integrable on that compact set. So this is well defined and it makes sense. So now if you we endo C infinity of omega with the following topology. Okay, so we will henceforth call C infinity of omega. So notation, we will call it E of omega. Just as we call D of omega for C infinity functions with compact support, E of omega is all C infinity functions. So psi n goes to 0 in E of omega if for every compact subset K contained in omega, okay, we have psi n and d alpha psi n for all alpha converging uniformly to 0 on K. So this is similar to the d omega convergence, but only now you see, because you cannot assume that the supports are all in some fixed compact set. That doesn't happen because the functions themselves don't have compact support. They are C infinity functions, and therefore on every compact set we say that psi n and all the derived sequences go to 0. So if you think, then it is very easy to see that d of omega, of course, is contained in E of omega. It is a subset, and it is also continuous, because if phi n goes to 0 in D of omega, that means all the supports are in a fixed compact set and their psi n and all the derived sequences converge to 0 uniformly. Any other compact set will either be intersect with this, or it will be disjoint, where the psi n's and phi n's will all be 0, and therefore this implies that phi n goes to 0 in E of omega as well. Just think about it a little, it's a very trivial thing. Okay, and therefore we say that d omega is continuously included in E of omega. Okay, and this topology on E of omega is again a Frechet space, which means it is induced by some metric, and therefore continuity of linear functionals. So continuity of linear functionals on E of omega is also decided by sequences. Okay, so now if you took, so if support of F equals K compact, then you look at psi going to integral over omega F psi dx. Okay, then this is because if psi n goes to 0 on E of omega, okay, then automatically it implies that all these go to 0 uniformly, F is integrable, and therefore you have on the compact set, on any compact set, in particular the support of F, which is K, and therefore this implies that integral F psi n on omega dx also goes to 0. Because it does so, all of them convert to 0 uniformly on the compact set, and therefore you have this immediately. Okay, so now so if so TF extends as a continuous linear functional on E of omega. Okay, now this is true, same is true for any T in D prime omega, support of T compact. So let us see how this happens. Okay, so let T belong to D prime of omega and support of T equal to K compact. So you can find phi 0 in D of omega such that phi 0 is identically 1 on K. So we have seen this on the very first day, this thing. Now if you take any phi in D omega, look at T of phi minus T of phi 0 phi. So by linearity, this is T of 1 minus phi 0 into phi. But support of 1 minus phi 0 into phi, where does it lie? It has to lie in k complement, because on k this phi 0 is identically 1, and therefore 1 minus phi 0 phi is 0. Therefore if at all it is not 0, it has to be this, so it has to be contained in k complement, and therefore this implies that T of phi equal to T of phi 0 phi. So in fact, if you have the support of T is compact and take any function in d omega which is 1 on k, then we have T is equal to phi naught of T in the notation which we introduced for multiplication by a C infinity function. Okay, so now you take any psi in E of omega and define T of psi equals T of phi naught psi. This makes sense because support of phi naught psi is contained in k, which is, and it is compact, and therefore this is a C infinity function with compact support, and therefore this defines the distribution. And of course if you have that if psi n goes to 0 in E of omega, this implies that phi naught psi n goes to 0 in d omega, because now all the supports are on the fixed compact set k. Phi naught is a C infinity function, and therefore by Leibniz formula, so it's all its derivatives are bounded in k, and therefore you have that phi naught psi n will go to 0 uniformly, because psi n goes to 0 uniformly with all its derivatives on any compact set k. In particular it will do it on this support of T, and therefore this goes to 0, and therefore you have that this implies that T is a continuous linear functional on E of omega. Now what about the converse? So conversely, let T tilde be a continuous linear functional on E of omega. Okay, so we already saw that if phi n goes to 0 in d of omega, this implies that phi n goes to 0 on E of omega and therefore that is d of omega is continuously included in E of omega. Okay, so T restricted to d of omega is a distribution. It's a continuous linear functional on T tilde. Okay, so we call this T tilde restricted to d omega, we call that as T. So T is a distribution. So claim T has compact support. So if not, we can write omega as the union Kn compact and Kn contained in Kn plus 1 for all n. So it's an increasing sequence. So you have omega here, and I can take an increasing sequence of compact sets which cover ultimately omega. We have already seen this when we proved that if integral f phi is 0 for every phi in d omega, then f has to be 0 for a locally integrable function. At that time, in the second step of the proof, we already used this fact. We constructed omega as the increasing union of relatively compact open sets. So you can make them also take the closures of those sets, so then it becomes the increasing union of compact sets. Okay, so then you can do this. Now if phi if T does not have compact support, then it cannot vanish on the complement of any kn. Okay, so for every n there exists a phi n tilde such that T only, T of phi n tilde is not 0 and support of phi n tilde is contained in omega minus kn. And so you normalize, you divide by this number, so you get there exists phi n, support of phi n contained in omega minus kn. So phi n tilde in d omega, of course. Okay, T of phi n equal to 1 and phi n belonging to d of omega. Okay, so we can have such a thing. Now we will get a contradiction. So if K is any compact set, contained in omega, then this implies that K is contained in Kn for n sufficiently large. Okay, and now the support of phi n is contained in omega minus kn, so this means that phi is identically equal to 0, phi n is identically 0 on K for n sufficiently large. And that means, for every compact set, after some time phi n becomes 0 on that compact set, and therefore phi n and all its derivatives go to 0 trivially, and therefore this says that phi n goes to 0 in E of omega. So this implies T tilde phi n, which is the same as T of phi n, goes to 0. But on the other hand, T of phi n is equal to 1, T of phi n goes to 0, so you have a contradiction, and therefore T has compact support. So we can also show exercise d of omega is dense in E of omega. It's very easy to show that, and therefore you have the extension of a distribution with compact support to E of omega is unique, because you are on a dense subset, you are extending it to the whole thing, so it's going to be unique. Therefore we can identify distribution with compact support with the dual space of E omega. So we have the following notation: E prime omega equals all distributions with compact support. Okay, so we will look at some other properties of distributions with compact support subsequently.